Hi, I'm Zor. Welcome to Unizor Education. I have already made a couple of lectures about Noether Theorem and put it on the website. But I would like to rearrange it a little bit because I think that it's very important to be more precise when using certain terms. Primarily, two particular words, symmetry and transformation, which are used in physics and in particular in Noether Theorem quite deliberately. I think I would need to put some more mathematical clarity to these particular terms. So this lecture would actually be preceding the ones which I have already recorded, and its purpose is to put on a more rigorous, more mathematical, if you wish, basis these words, symmetry and transformation and continuous transformation, etc. So this lecture would be like introduction, if you wish, into those lectures which I have already recorded and maybe some others. Again, its purpose is to be a little bit more precise with whatever we are talking about in Noether's theorem. So this lecture is part of the course called Physics Plus for all, and it's all part of the Unizor.com educational website. Website is totally free. There are no advertisements. You do not have to subscribe, or you can sign in, but that's actually not really necessary. It's all optional, and it serves some other educational purposes. If you don't want to sign in, don't. So you can use the website totally free. It's ready when you are. Now this lecture is part of the course, as I said, Physics Plus, and there are other courses. There are prerequisite courses. There is a Math for Teens, for example, Physics for Teens, and there are other courses like Relativity, which you can also take if you wish. Okay, so let's get back to symmetry and transformation. Again, my purpose is to clarify these two terms in a more mathematical way. Okay, so first of all, one statement actually about Noether's theorem. Now, by the way, the Noether theorem was regarded by many famous physicists like Einstein and others as one of the most remarkable achievement, although it's not really very complex or anything like that, but it basically puts the laws of conservation, which we all know about in physics, on a more logical foundation, I would say. So we don't take the law of conservation as given. It actually follows from certain, if you wish, geometrical properties of our time and space. So in particular, if time is uniform, then the law of energy conservation would follow. As a consequence, not as an axiom. So the axiom should be in the uniformity of time, and then the laws of conservation follows. And again, if it's not uniform, if time is not uniform, then we don't really have this particular law of conservation. It seems to be more fundamental. The geometrical properties of our time and space seems to be more fundamental than the law of conservation of something, of energy or momentum or whatever. And it's easier logically to accept the uniformity of time and space and direction, etc., accept it as axioms, than to accept as an axiom something like the law of conservation of energy. So, at least my personal opinion is that the axioms, which we are taking basically without any kind of proof, because it cannot be proven from anything more fundamental. So the axiom must be as elementary as possible. So the geometrical properties of our space and our time are more fundamental than the law of conservation. Again, in my point of view and in many others actually viewpoints. Same thing as for example we took as an axiom the second law of Newton. Force is equal to mass times acceleration. I mean, it's from experience, and we're just basically taking it. Or equivalent, we can take in Lagrangian mechanics, we can have another approach, we can have action, etc. So that's what I wanted to say about this Noether theorem's philosophy, if you wish. It puts something on a more fundamental basis than before. So the way how it can be actually stated is that Noether theorem establishes certain relations between invariances of physical laws, like invariance of the energy, for example, and certain quantities which are preserved during the motion. And these are quantities which are related to whatever the motion is, like energy or whatever. So certain uniformity or certain invariability of our space and time are the fundamental for certain conservation laws. So that was a great achievement of Emmy Noether. Okay, now let's talk about something which we have already learned, and I would like just to mention these particular things because I'll just use it during this lecture. So the prerequisite which you have to be familiar with are well, the concept of a configuration space of the mechanical system, and I'm using using the coordinate something like Q, which is Qi for I from I1 to n. It's n-dimensional, and is basically the degrees of freedom of a mechanical system. So these are generalized coordinates, so they make up the configuration space. Now the second thing is Lagrangian, so you have to know what that is, and that's all in previous lectures. It's basically a function of certain functions. Time, generalized coordinates and their derivatives. So the form of Lagrangian in some simple cases is kinetic minus potential energy, and in simple cases it doesn't really depend explicitly on time. So this is all in the previous lectures about Lagrangian, previous chapter actually of this course. Also I would like you to know that there is a action functional which depends on trajectory, and this is integral from the beginning to the end of trajectory of Lagrangian. So I presume this is known. And considering this is a functional, which means a function of a function, the real trajectories of real objects moving are actually stationary point of this functional, and to derive these real trajectories we need the Euler-Lagrange equation, which looks like this. Apostrophe is derivative, time derivative. For each dimension. So this is basically the Euler-Lagrange equation, solution of which are stationary points for this functional and can be real trajectories. And solution to this is exactly the same as solution for second Newton's law, where A is the second derivative of Cartesian coordinates of the object. So in Cartesian coordinates, this is working. In generalized coordinates, we need to resort to Euler-Lagrange equations, where Q is not necessarily Cartesian coordinates, although it can be, but might be something else. So these are basically, this is in Cartesian coordinates and this is in generalized coordinates, they are equivalent. So these are something which I presume you have to know, although I will not use basically these formulas right now in this lecture, but in further lectures about Noether theorem they will be used. Okay, so this is just a preliminary kind of words about certain amount of knowledge which you have to possess before learning about Noether's theorem. Next I will go into more philosophical kind of part. As I said, I would like to define symmetry and transformation in a more rigorous way. So let me start from a general understanding of what is symmetry. Well, symmetry is something which actually makes two different objects similar in some way. They look alike, maybe. Now, example, for example, if you have two squares, this one and this one is the result of rotation around the center of the first one. Are they similar? Well, in some way they are similar. There are certain elements which are similar, like the length of the side, like the area or perimeter. What they are not similar in, they are not similar in their position relative to, let's say, system of coordinates. Position is different. Angle towards, for instance, x-axis is changing. So there are certain properties which we are interested in. They might or might not be similar in two different objects. Okay, so this is kind of a philosophical thing. Now, in a more, just one step towards more rigorous explanation of this. Whenever we are talking about two different objects and their similarity in some way, we usually talk about certain transformation of one object into another. For example, if you have two triangles, let me put it this way, one triangle and another triangle. How should I say we are similar? We are saying they are similar relative to the axis between them, right? Well, what we actually think about in this particular case, we think about this way. If I will take this piece of the plane and just fold it onto this one, then this triangle will coincide with this, and that's what makes it similar. So similarity is always related to some kind of transformation. Like in this case, it's a rotation. I'm rotating one square around the same center point to get into the position of another square. So similarity almost always should be considered in relationship with certain transformation. So its transformation of one object into another kind of produces certain similarity if it's a, well, good transformation. Now, obviously, transformation of this triangle into this triangle, it's not really transformation per se. I mean, yes, it's changing, but nothing is retained. The sides are different, area probably is different as well. Although we might consider, for example, transformation from this to this, which retains the area, maybe, but it's less interesting, let's put it this way. So, again, transformations and symmetries are related. Transformation produces another object which is similar or not similar to the original object. All right? So that's very important. Now, speaking about this rotation, for example, we can rotate by any angle phi between these two. This is angle phi. Now, if I rotate by any angle phi, my sides are retained, so sides can be considered symmetrical. My area and perimeter are, but position relative to the axis is not. However, if phi is equal to 90 degrees, even my position relative to the other to the axis of coordinates will be the same, right? If we will take one particular square and turn it by 90 degrees, it will basically turn into itself. So certain transformations can be defined as continuous, like if I'm just turning by any angle phi. That would be a continuous transformation for any angle, which means angle phi can be actually any value. But certain transformations, which again retain certain qualities, should be discrete. So the transformations which are preserving everything, including the position, is discrete by 90 degrees or its multiples. But transformation which retains only, let's say, the length of the side can be by any angle. So these transformations can be actually continuous. Again, this is philosophical kind of explanation. So in Lagrangian mechanics, we are interested in physical mechanical systems, and what is the property? Like in this particular case, square has a property which is length of its side. What is the property of mechanical system which we can consider to be preserved during the motion? Because everything, whatever I was just saying about, it's all related towards future usage of this apparatus for mechanical system. Well, in case of Lagrangian mechanics, what we are interested in is action functional. So action functional is basically totally describes the system, if you wish, because the mechanical system and its movement, that's what I want to say. Because trajectory is one thing, but trajectory does not really necessarily define everything, define the motion. Well, what if you have a particle moving along a straight line? Well, straight line is trajectory, but it doesn't really define the motion because the motion can be back and forth or with different speed, etc. To have the motion and basically to encompass the whole movement of the mechanical system, action functional defines basically everything, because we can, if we know the action functional, then we can actually calculate its stationary points, and these are where the system mechanical. This is how mechanical system is moving. So one particular characteristic of a motion is action functional. It's an integral, as I was saying before, on an entire trajectory, so it encompasses in itself as one particular number, numerical, real number. It describes basically the whole movement in some way. So preservation of this particular action functional is something which we would like actually to analyze in Lagrangian mechanics using this concept of symmetry and transformation. So we will use the concept of transformation to reflect the motion of the mechanical system, and preservation of this particular action functional would be a symmetry, if you wish, or invariance, which we are looking for. Okay, so that actually is the purpose of Noether's theorem to analyze under what circumstances we have this particular symmetry and what follows from it. So if something like action functional is preserved, then we can talk about certain symmetry and make certain derivations, if you wish, of physical laws from this. Okay. Next, let's try to mathematicize whatever this concept of transformation. Now, what is transformation? Well, if you have certain object, a mechanical system, let's call it omega, it's transformed into another object, Q1, whatever. Now, then, if we are talking about transformation, we probably can apply transformation to this object to get some other object, etc. So we are talking about if we are talking about transformation, we really talk about certain set of objects transformed from one to another by certain transformation T. Okay, now, again, our purpose is to reflect mechanical motion. We can move it a little bit or we can move it a lot. So transformations can be different. Transformations are actually not only a function of object, but also a function of how we transform. And so to make it a little bit closer to mathematics, we need some parameter by how, so this is what we are moving, and this is how we are moving. That's what transformation actually is. So this particular transformation, which I kind of put a little shorter, omega with epsilon over there. So this is transformations which we are talking about. So it's a class of objects first, and transformation which we are talking about, this type of transformations, are defined within this class. So for any object of this class, we can transform it with certain value of epsilon to another object. And then other object can be transformed to something else, etc. But we are still within this set of objects. We are still within the set of positions of our mechanical system, if you wish. So transformation is a movement from one point to another, from one position of mechanical system to another, to the next position after the movement. So this is what we are transforming. Epsilon gives us parameter which tells us how we transform it, by this much or by certain amount of time or something. So there is some parameter, numerical parameter, which actually is defined for any transformation. So transformation depends on what we transform and how we transform, or by how much we transform, if you wish. And that's the result. This basically gives you a little bit more mathematical concept of what is a movement. So we are trying to put a physical concept of motion into mathematics of certain object and certain group of transformations. Now, I mentioned just the word group. That's very important. Another important concept is continuous transformation. Now, what is continuous transformation? We were talking about the square when we are rotating it by angle phi, and it can be anything, maybe small, maybe large, etc. But what's important is if we turn it a little bit, it changes a little bit, right? Okay, how can we again put mathematics into it? What is changing in the object, in the system? Well, there is certain property of this object which must be changed, maybe a little bit. In case of mechanical system, that's an action functional. So if we are applying transformation to an object, certain property, let's put it P of omega, So its property is defined for every object in the class, for all Q1, Q2, Q3, everything. So for object and for its image, which is another object, for all the objects, property should be defined. And that's what's important. That's what continuous is actually very important, and it reflects the physics of the whole process. If I change a little bit, so if epsilon is very small, my property also should be property of the Q minus property of the Q epsilon. They also must be small. So if this is infinitesimal variable, then the difference in the property after the transformation using this epsilon should be infinitesimal. So the transformation T. Now instead of this I can put obviously T of epsilon comma omega. Okay? So if from infinitesimal epsilon follows infinitesimal change of the property, then we can say that the transformation is a symmetry relative to this particular property. But that must be true for any object in the whole class. So if we have this property that transformation of any object within the class has the property of changing changing certain property P infinitesimally if epsilon is infinitesimal, then we're talking about continuous transformation. Continuous transformation changes the particular property a little bit if it's a small transformation. Small transformation is a small epsilon, and obviously this is the difference between property of the object and the property of its image after the transformation should be also infinitesimal if epsilon is. Okay, now let's talk about the word group I was talking about. So transformation must be, all the transformations must be a group. What does it mean? Well, primarily it means the following. Let's talk about transformation of this type. So what if epsilon is equal to 0? Now I would like this to basically not change the object. If I'm moving my mechanical system by 0 meters, or the time where mechanical system lives changes by 0 seconds, the mechanical system should not change, right? It does not. It doesn't change position, doesn't change in time, etc. So this is identity. So all the different t's, whatever we are talking about, for all the different epsilons and for all the different objects, if epsilon is equal to 0, it should be identity. It should not change the object. So change by 0 means no change. So that's one of the properties which makes it a group. Another property is if you have a composition. Again, let's talk about time. Here is the system. Now, what if we have this system, let's say a couple of seconds ago, and then let's move it forward a couple of seconds. It will be in the same position. Or if we will move it forward by a couple of seconds and then consider the time going back, like you have the movie you can put in reverse. First you put it forward and then you move it in reverse. It should actually be in the same position after this. So my point is that if you apply epsilon first, and then that would be a q epsilon. But let's talk about, instead of epsilon, we'll use another letter, we'll use alpha. And then you apply beta to to your object, which is the result of first one, to alpha. So first you move it by alpha and then by beta. It's supposed to be, so let's put it this way, it's supposed to be the same as you move it by alpha plus beta. So I hope this is understood. Let me put it geometrically. Again, it's all related to physics, to the motion. If you move by 1 meter and then by 3 meters, it's the same thing as if you will move by 4 meters, right? So that's what basically it's all about. So if you have an object Q, object omega, okay, you put it as t of alpha omega into omega alpha. Then this omega alpha you put it with t beta omega alpha to omega gamma. Now, and here you put 2 of alpha plus beta, the same object, and you will get exactly the same thing. So gamma is equal to alpha plus beta, if you wish. So that's my point. So this is a property which makes all the transformations t of alpha omega, for any omega, for any alpha, it's a group. That's what I would like to say. So which means t of 0 omega is identity, t of let's say alpha omega, and then combined with t of beta omega must be preserved, well, meaning to the result of the first one, t of alpha plus beta omega. So that's what makes it a group. Now, let me summarize the whole thing. We are talking about a modeling of the motion with certain mathematical apparatus, and we need this to define it in such a way that transformations must be continuous, must be defined for the whole class of objects omega. Within this class they should not really go outside. They must be a group of transformations, and we are talking about only continuous transformations because we need it for mechanical purposes. Basically that's it. So thanks very much, and read the notes for this lecture on Physics Plus. That's very important. I think you will understand it much better, and the future lecture will be on a good mathematical foundation. Good luck!